Hello students, welcome to Memo Neet. This is your physics teacher. And in the last video, we discussed about magnetic effect of current, in which we studied Biot-Savart's law, we studied Ampere's circuit law, we studied about solenoid, we studied about force on a moving charge in a uniform magnetic field, and all these topics. I hope you practice the questions and you have done the solutions for all the questions. Practice them, and the concepts are clear to all. I always request you all to see the video and comment if you have any doubt or any problem in the uh, video or the explanation being given to you, right? So please you have a good use of the comment box below. Write your comments, give your feedback so that we can improve in making you all understand better the concepts of the chapter, right? So in the second part which we are going to see today is the magnetic effect of current. The second part we are going to see, the very first topic is the force experienced by a current carrying conductor in a uniform magnetic field, right? So in our last lecture we saw that the force exerted on a uniform on a charge moving in a uniform magnetic field was given by F vector was equals to Q into V vector cross B vector, right? So suppose there is a conductor which has its area of cross section as A and length as L, and small n is the number of free electron per unit volume per unit volume. Then n, capital N, will be the total number of free electrons in it, and that will be equals to n into A into L. So the total charge flowing in a conductor if a battery is connected across it, that will be equals to your N into A into L into E. This will be the total charge flowing in the conductor, right? And the conductor will be moving with the velocity of Vd. The velocity would be Vd, right? So if I write it like this, that force on n number of electrons flowing in a conductor when placed in a uniform magnetic field will be equals to n a l e, this is equals to q, into vd cross b. So what we are doing here is we are calculating the net force acting on the conductor because all the free electrons in it, and this would be nothing but equal to the force experienced by the conductor, right? Force experienced by the conductor in a uniform magnetic field will be equal to the force experienced by all the free electrons flowing in it. So we can write F is equals to, now from here we can say that this, if uh, we find the cross product, we write N E A L V D into B into sine theta, where theta will be the angle between the velocity vector and B vector, right? So from here we can say that F is equals to this NEAVD is nothing but I, as we saw in current electricity. So I into B into L sine theta, right? So from here we can say that F vector is equals to I into L vector cross B vector, right? F is equals to L vector cross B vector. Where taking L vector is basically the direction of the current. So the force on a current carrying conductor placed in a uniform magnetic field is given by F is equals to I into L vector cross B vector, right? And this expression will give you the magnitude of the force. And to find the direction of force, we will use Fleming's left hand rule, in which the index finger will be in the direction of the magnetic field, right? The middle finger will be in the direction of the flow of current, and thumb will indicate the direction of force, right? So if suppose magnetic field is vertically inwards and the current in the conductor is flowing in this direction, then placing the index finger in the direction of magnetic field, middle finger in the direction of the current, then the thumb will indicate the direction of force, that will be in the upward direction. This is F, then this is your I, this is B, right? So you get force in the upward direction. So this is how you will be finding the direction of the force experienced by the current carrying conductor placed in a uniform magnetic field, and the magnitude is being given by F is equal to IBL sine theta, right? Now to understand it well, let's solve a numerical. Let's see this numerical. The first numerical says that a straight wire of mass 200 gram and length 1.5 meter carries the current of 2 ampere. It is suspended in mid-air by a uniform horizontal magnetic field. What is the magnitude of the magnetic field? Right now, see if suppose this is the conductor, right, and if it's being suspended in the air, then definitely the net force on the body is zero. So the forces acting on the body is, one is the weight of the body, that is mg, and another weight is the magnetic force F, and this is being suspended, remain suspended in the air only if when magnitude of F is equals to mg. Now, if we take the direction of current in this direction, this is the direction of current. So, using Fleming's left hand rule, if we place our fingers in the direction of current and in the direction of force, what we'll find that the magnetic field is moving is in the direction inwards the plane of the paper, right? So, this should be the case, and F should be equals to mg. What F will be equals to? F will be equals to I B L sine theta, and this has to be equals to m into g. Theta over here we can see theta is equals to 90 degree. Theta is equals to 90 degree. Therefore, we'll get I B L is equals to mg. So, what they are asking is the magnitude of the magnetic field. So, from here we'll get V is equals to M is 0.2 into G. We will take it as, let's take it as 9.8, right, upon I is 2 amperes into L is 1.5, right. Then solving this will give us this F is equals to, will give us 0.65 Tesla. Solving this will give you a 0.65 Tesla. So this is the magnitude of magnitude. So what is happening over here? The body is in equilibrium, and it is in equilibrium because the weight of the body is being balanced by the magnetic force experienced by the current carrying conductor in the uniform magnetic field. So we just equate them and solve it. From there we get the magnitude of the magnetic field. We have already mentioned the direction, that the direction is in the vertically inwards the plane, inside the plane of the paper, right? How we found it? We found it with the help of the Fleming's left hand. Now let's see one more numerical. It says a short conductor of length 5 centimeter is placed parallel to a long conductor, right? The total is, yeah, parallel to a long conductor of length 1.5 meter near its center. The conductor carries current of 4 ampere and 3 ampere respectively in the same direction. What is the total force experienced by the long conductor when they are 3 centimeter apart? So, there are two conductors. One conductor is a long conductor and another conductor is a short conductor. Let the current flowing in the first conductor be I2 and the current flowing in the short conductor be I1, where according to the question, I1 is equals to your 4 ampere, that is 4 ampere is flowing in a short conductor, and I2 is equals to 3 ampere, that is the current flowing in the long conductor. Long conductor is of 1.5 meters and the short conductor is of 5 centimeters. So we can easily see that 5 centimeters is very small in comparison to 1.5 meters. So in comparison to the short conductor, we can say that the long conductor is of infinite length, right? So if I calculate the force on the short conductor because of the long conductor, that force will be equal to the force experienced by the long conductor as well, because here it will be an action reaction pair. So the force experienced by both the conductors will be same, but they will be in opposite direction. The magnitude will be same, but the direction will be opposite. So for the short conductor, the long conductor is an of infinite length. Then the magnetic field for an infinite length conductor we saw in our first lecture is given by mu naught I upon 2 pi r, right? Mu naught I upon 2 pi r. So the magnetic field experienced by the first conductor is because of the current flowing in the second conductor. So it will be I2 here, right? So on uh, force on this first conductor, that is small conductor, will be equals to the magnitude will be equals to I1 into B into L into sine theta, right? So this will be equals to I1 into mu naught I2 upon 2 pi r into L into sine theta, right? So sine theta here, if we see that the magnetic field because of the long conductor for the small conductor, it will be using Maxwell's right hand thumb rule. So if the current is in the upward direction, the magnetic field will be in inward direction. So the magnetic field experienced by the short conductor will be a magnetic field which is inverse, right? So if the magnetic field is inverse and current is going in the upward direction using Fleming's left hand rule, the direction of the force will be in towards the left, right? Similarly, for the long conductor, the magnetic field will be in the outward direction, right? The magnetic field will be in the outward direction, outward direction. So using Fleming's left hand rule, the current is flowing in the outward direction. Sorry, the magnetic field is in outward direction. The current is flowing upward, so the force will be in towards the right direction. So it will experience the force in this direction, right? Both the forces are the same magnitude, but they have different direction. So from here we can say that the force experienced by the conductor F will be equals to mu naught I1 I2 upon 2 pi r into L and sine theta here theta is 90 degrees, so it will be uh, 1. So putting the values of the variables over here, we will get we will get F is equals to 4 pi into 10 to the power of minus 7. Let me F is equals to 4 pi into 10 to the power of minus 7 into I1 and I2 are 4 into 3 upon 2 pi. R is how much? 3 centimeters. So 3 centimeters will be 3 into 10 to the power of minus 2 into L, right? L is of, right? L is of how much? L is of 5 centimeters. So it will be 5 into 10 to the power of minus, right? 5 into 10 to the power of minus. So this 5 into 10 to the power of minus 2, 10 to the power of minus 2 goes off. This 3 and this 3 goes off. and then this 2 pi and 4 pi gives you 2. So 4 twos are 8 and 5 are 80. So 40. So which is equals to 40 into 10 to the power of minus 7 Newton, right? 40 into 10 to the power of minus 7 Newton. So we can say that the force experienced by both of the conductors will be equal to F is equal to 4 into 10 to the power of minus 6 Newton, right? So this would be your answer. Correct. So now let's move forward with another concept. This is what is current. When a current carrying conductor is placed in a uniform magnetic field, it will experience a force. Now moving forward with the numerical, moving ahead with the numerical, which we saw just now, with the same concept. If we say that there are two conductors, right? There are two conductors of infinite length. Let's say this. This is conductor one. This is conductor two. Current in the first conductor is I1 flowing in the upward direction. Current in the second conductor is again I2, right? And the separation between them is, let's say, R. Then, in this case, both the conductors will experience the same magnitude of the current, but the direction will be different. And that magnitude of force per unit length is given as F upon L is equals to mu naught I1 I2 upon 2 pi R, right? 2 pi R. This is the same formula which I used in the last numerical we discussed just now, right? So this is the formula for force per unit length for a two infinite length conductors placed close to each other. Now, if I talk about the direction, if we consider the magnetic field because of the first conductor, experienced by the second conductor would be, so the current flowing in the first conductor is in upward direction. So using Maxwell's right hand thumb rule, the magnetic field experienced by the second conductor will be in the direction inside the plane of paper. Now, if the direction of magnetic field is inside the plane of paper and the current flowing is upward direction, so the force experienced will be left hand side, which is with the help of Fleming's left hand rule. So this will be the direction of force experienced by the second conductor. Now, if we talk about the first conductor, so the magnetic field experienced by the first conductor is because of the second conductor. So, if the current flowing in the second conductor is in upward direction, then the magnetic field at first conductor will be outwards direction with Maxwell's right hand thumb rule. So, the magnetic field experienced by the first conductor is in a direction outwards the paper, right? Now, if the magnetic field is in outward direction, current is flowing in the upward direction, then by Fleming's left hand rule, the force experienced by the conductor will be in right direction towards the right hand side. So this will be the direction of force. So what we find here is that when the two infinite length conductors are having current in the same direction, they experience a force per unit length of magnitude given by mu naught I1 I2 upon 2 pi R, where R is the separation between the conductors, and the direction is that the forces are attractive. When the current flow in the same direction, the two wires attract each other. Now coming to different case, the different case is that when two conductors are having the current in the opposite direction. Suppose in the conductor 1, the current flowing is in upward direction, and in conductor 2, the current is flowing in the downward direction. See, again the magnitude of the force will be, so F by L will be equals to mu naught I1 I2 upon 2 pi R. But if we talk about the direction, because of the first conductor, the magnetic field experienced by the second conductor will be again in the inward direction, right? It will be in the inward direction. Now, if it is in the inward direction, using Fleming's left hand rule, placing the index finger in the direction of magnetic field and middle finger in the direction of current, we find that the force experienced by the second conductor will be in the direction right hand side. So it will be experiencing force in this direction. That is, this is F, right? Now, for the first conductor, the magnetic field experienced by the first conductor is because of the second conductor, and because of the second conductor, the current flowing in the downward direction by Maxwell's right hand rule, the magnetic field will be in inwards direction, right? Magnetic field will be in inward direction. So here also the magnetic field will be in inward direction. Now, using Fleming's left hand rule, the direction of force will be given as magnetic field is in inward direction, right? Current is flowing in the upward direction, so the force will be in the left hand side. So the force experienced by the conductor first will be in the left hand side direction and the magnitude being same and the direction being opposite. What we can see here is when the current flowing in the two conductors place close to each other and the current direction of the current is in opposite direction, the conductors repel each other, right? So when the current is flowing in the same direction, the conductors attract each other, and when the current is flowing in the opposite direction, the conductors repel each other. And the magnitude of the force per unit length is given by the formula mu naught I over I 2 upon 2 pi r, right? 2 pi r. This is how we calculate the force per unit length because of the two conductors having current in them placed when placed close to each other, right? Now let's come to the next topic, which is torque. Torque experienced by a coil placed in a uniform magnetic field. Now, suppose this is a coil or rectangular coil which is placed in a uniform magnetic field and it has its length as it's a square coil, right? Having all its size as A, right? And it's placed in a uniform magnetic field. Let's say there is a magnet here, it is north, and here it is south. Let's say like this. So the magnetic field in this direction, and the current flowing in the coil is in clockwise, anti-clockwise, right? So let the coil be named as A, B, C, D. So what we find is that the conductor AB and BC, they experience the magnetic force in the direction which will result in no motion of the conductor, right? That is the force experienced by both the conductors in the horizontal plane, like this AB and AD and BC. The net force on them will be equals to 0. But when we look into the conductors AB and BC, what we see that for conductor AB, the magnetic field is in this direction, that is from my right, from my left to right, and the current is going in the downward direction, and the force experienced by this conductor will be in an outward direction, right? It will be in outward direction. Whereas coming to the conductor DC, the force experienced by the conductor DC is magnetic field is in the left to right direction, current is flowing in the upward direction, then the force experienced by this conductor DC will be in inward direction, right? It will be in inward direction. So suppose this is the coil placed in the magnetic field. Magnetic field is from my left to right. Then this conductor will be experiencing a force in outward direction, and this conductor will be experiencing a force in the inward direction. So what will happen? This will turn. This will turn and it will experience a torque. So if I show the torque, if we view the coil from the up from the top, what we'll find that this coil is experiencing force F, sorry, is experiencing force F in this direction and this F in this direction, forming a couple. So if this is the line of action and this is the magnetic field B vector, this F vector, F vector, and the angle between the coil and yeah, the coil and the magnetic field is theta, then if I join this like this, hold on, okay, let me draw it again. If this is the coil, this is one of the force F, this is the another force F, right? Then joining this, if this is the vertical and this angle is theta, right? A magnetic field is in this direction. Let's say it is in magnetic field is in this direction, right? This is magnetic field B. Now, very first thing which we need to know is if these are the two lines of action, then the shortest distance between the line of action is this. This line is the shortest distance. So this line will be equals to, if this is the length of the coil which is equals to A, then this will be equals to A sine theta, which is R, and the magnitude of F is F. So the torque will be equals to A sine F into A sine theta. F into A sine theta. Right? Now, if I draw a perpendicular from here, what we can see that this perpendicular is nothing but the area vector. This perpendicular is nothing but the area vector of the coil. This area vector of the coil will also make an angle of theta with the magnetic field. It also makes the angle theta with the magnetic field. So, putting the values, that is for tau, putting F is equals to IBL, then A is the width and into sine theta. So L into A will give you the area. So tau will be equals to I into B into A into sine theta. Now I into A is nothing but magnetic dipole moment. That is tau is equals to M into B into sine theta. What is M? M is known as magnetic dipole moment, which is equals to I into A vector. I into A vector. So the direction of the magnetic dipole moment is in the direction of the area vector of the coil. So from here we can say that tau is equals to M vector cross B vector. M vector cross B vector. Right? So in the formula, that is tau is equals to mb sine theta. The theta is the angle between the magnetic dipole moment and the B vector, and magnetic dipole moment has a direction in the direction of area. So theta will be the angle between the area vector and the magnetic field vector, right? How the area vector is? We know that area vector is always perpendicular to the plane, Now understand, if the magnetic field is moving from my left to right, and I am placing a coil like this, that is, the coil is perpendicular to the direction of magnetic field, then the area vector and the magnetic field vector has an angle of 0 with each other, right? And in this case, the torque on the coil will be 0. Now, if I place my coil like this, then in this case, the magnetic field and the coil has an angle of 0 degree, but the magnetic field and the area vector of the coil makes an angle of 90 degree with each other. And in this case, the torque experienced by the coil will be maximum, right? So depending upon the angle between the area vector and the magnetic field vector, we will decide the magnitude of the torque experienced by the coil. So I repeat again that in the formula, tau is equals to mb sine theta. Theta is the angle between the area vector or the magnetic dipole moment vector and the magnetic field vector, right? So let's see one numerical for this. See, it says calculate the torque on a 100 turn rectangular coil. 100 turn rectangular. So let me tell you one more thing over here, that if torque is being given as tau is equals to mb sine theta, then for here the number of turns in the coil is 1. So if the number of turns in the coil is capital N, then the total torque will be equals to capital N into M B into sine theta, right? M B N M B sine theta. So here in the question, it says calculate the torque on a 100-turn rectangular coil of length 40 centimeters and breadth 20 centimeters, carrying a current of 10 ampere when placed making an angle of 60 degree with the magnetic field of 3 Tesla, right? So see, what they have given to us is number of turns is equals to 100. Now if we calculate the area of the coil, it would be equals to 40 into 20 into 10 raised to the power of minus 4 meter square. This is the area. Then the current flowing in it is I is equals to 10 amperes, right? And the angle which coil makes with the magnetic field, it means that if this is the magnetic field B, then this is the coil and it makes an angle of 60 degree, then its area vector which is perpendicular to the coil will be making an angle of 30 degree. I hope I made it clear. So here the theta will be equals to 30 degrees, not 60 degrees, and the magnetic field B is equals to 3 Tesla. What they are asking us to is calculate the torque. So we have the formula tau is equals to N into I into A into B into sine theta, right? So this will be equals to 100 into 10 into 40 into 20 into 10 raised to the power of minus 4, right? This is area into 3 into sine 30 is 1 by 2, right? Sine 30 is 1 by 2. Solving this will give you the torque is equals to 120 Newton meter, right? It will be equals to 120 Newton meter. So again what we find here is that we can, if you remember the formula well, we can simply put the values and get the answer. Remembering that if they say that the coil is making an angle of 60 degree with the magnetic field, it means the coil is making, it's not the area vector which is making. So if the coil is making an angle of 60 degree, then the area vector of the coil will be making an angle of 30 degree. Means the angle made by the coil is complementary to the angle made by the area vector with the magnetic field. And we have to use the angle between the area vector and the magnetic field in this where is the as the value of theta, right? So the answer will be your how much 120 Newton meter. Now let's see one more numerical. There is yes, we can see it. It says no. Let's move forward. So this is how we calculate the torque experienced by a coil kept in a uniform magnetic field. Now we have seen that when we place a uniform magnetic field, a coil in a uniform magnetic field, it will experience a force. So we can utilize this in making it into a moving coil galvanometer. What we have in a moving coil galvanometer is that we have a arrangement with permanent magnet which provides us a magnetic field, a permanent magnetic field, right? And in this permanent magnetic field, we place a coil, we place a coil, right? Which when a current is flowing in it will experience a torque and will turn. Now if we attach a needle with it, right, and we mark 0 over here, and as soon as the coil experiences a torque, the needle will move from this point to a certain angle and it will show us some reading, let's say, right? Now once it has turned, we need this needle to come back, right? We need this needle to come back and restore its position. So what we do when we pivot this coil in the galvanometer, we fix it with a hair spring. Hairspring, what does this hairspring does? This hairspring helps this coil to restore its position once the current has been withdrawn from the coil. Once the current has been withdrawn from the coil, this spring will help the coil to return back to its original position, right? So if the current is flowing in the coil, the torque experienced by it is equals to N I A into B into sine theta, right? Now to keep this sine theta always equals to 1, there is a radial magnetic field used. For that we use a cylindrical permanent magnet which has its magnetic field along the radius, right? Now when it is so, or the angle between the area vector and the magnetic field vector is always 90 degrees. So to maintain the maximum torque experienced by the coil, we use a radial magnetic field, right? It is somewhat like this. Magnets are like this, right? And the field is in along the radius. So it is radial magnetic field. So here sine theta will always be equal to 1. This is the torque experienced by the coil. The restoring torque given by the spring, that torque is directly proportional to alpha. What alpha over here is? Alpha is the angle of deflection. Alpha is the angle of deflection. So to remove this proportionality, we get tau. We write it as PR, which is restoring torque. This tau R restoring torque will be equals to K into alpha. Right now, what is K? K is torsional constant. Right, as we have the constant for a spring, that is spring constant, the same way here we have a constant, right? So when we apply current in the coil will turn because of the torque experience. So one of the torque is acting in, let's say, is in clockwise direction, which is making the needle to move from 0 to some reading, and another torque, which is the restoring torque, is acting in the opposite direction, which wants to restore the position of the coil, right? Now when these two torque becomes equal to each other, what will happen? The needle will be in equilibrium and it will stop at a point where the reading is to be shown. So at equilibrium, what we have tau R is equals to tau, right? Tau R, that is the restoring torque, is equals to the torque experienced by the coil because of the current flowing in. So we can write A into alpha is equals to I B N A. I B N A. So from here we get K is equals to I B N A upon alpha, right? I B N A upon alpha. Yes, I B A upon alpha. Now the angle of deflection alpha is directly proportional to the current flowing in it, right? More is the current flowing in it, more will be the torque and more will be the deflection, right? More will be the deflection. So from here we can say that your we can also write this as alpha is equals to N B A upon K into I. Now this quantity NBA upon K, N is constant, it is the number of turns in the coil, turns made, fixed. The magnetic field, again it is fixed, area of the coil is again it's fixed for a given galvanometer, and K, that is the torsional constant, again it is fixed for the given galvanometer. So if this is fixed, we name this NBA upon K as galvanometer constant capital G, and this is fixed for a given galvanometer, right? So alpha is equals to Gi. Alpha is equals to Gi. Now, if I write it as alpha upon I, this will be equals to G. Wait a minute. All right. This is 1 upon G. This is 1 upon G. This is 1 upon G. So this will be equals to Gi upon G. Right. So this will be equals to 1 upon G, and this 1 upon G is known as sensitivity. Sensitivity, right? That is, it will give you degree per unit current, and if it is being calculated for current, it will be known as current sensitivity, right? That is, if it is showing a deflection to alpha for a current I, then this is known as current sensitivity, and if we write it as alpha upon V, then it will be known as voltage sensitivity, right? It will be equal to the voltage sensitivity. That is the number of degrees, that is degree per ampere, and this is degree per volt, degree per ampere and degree per volt. So if we see that if it is current sensitivity or it is voltage sensitivity, both have N B A upon K, right? And here it will be N B A upon K into R, right? So these number of turns B, A and K, these are the factors on which we can change the current sensitivity or we can change the voltage sensitivity. But it is difficult to change B and A, but it is easy to change the number of turns in the coil. So simply by changing the number of turns in the coil, we can change the sensitivity of the galvanometer, right? So the current sensitivity and the voltage sensitivity is number of, so it is the deflection per unit current or per unit voltage, that is degree per ampere, right? So to understand better the current sensitivity or the voltage sensitivity, let's solve a numerical. It says a rectangular coil of area 5 into 10 to the power of minus 4 meter square and 60 turns is pivoted about one of its vertical side. The coil is in a radial horizontal field of 90 G. 90 G. D is Gauss, that is 1 Gauss is equals to 10 to the power of minus 4 Tesla, right? 1 Gauss, 1 Gauss is equals to 10 to the power of minus 4 Tesla, right? So what is the torsional constant of hairspring connected to the coil if the current of 0.20 milliampere produce an angular deflection of 18 degrees, right? So what they have given to us is A is given to us is as 5 into 10 to the power of minus 4 meter square, right? This is the first thing. We have the number of turns N is equals to 60. Second thing is the coil is a radial horizontal magnetic field is being given to us. B is equals to, we'll write it as 90 into 10 to the power of minus 4 Tesla, and consider saying the current flowing is 0.2 into 10 to the power of minus 3 ampere, and alpha is equals to 18 degree. They're asking us to calculate K, right? So we know that K is equals to INBA upon alpha. So simply putting the values, we get K, that is torsional constant. K is equals to 0.2 into 10 to the power of minus 3. This is current into 60, is the number of turns, into magnetic field, that is 90 into 10 to the power of minus 4, which is the magnetic field. Area is 5 into 10 to the power of minus 4, this whole upon 18, and solving this will get the value of constant K as, we get K as 3 into 10 to the power of minus 9, 3 into 10 to the power of minus 9 Newton meter per degree, right? This is the value of the torsional constant for this given galvanometer, right? So again, putting the values in the formula, if you remember it, will give you the answer. What we have to remember is that in equilibrium, the restoring torque is equal to the torque experienced by the coil because of the current flowing into it, right? What is the restoring torque? Restoring torque is K into alpha, and the torque in the coil is I N B A sin theta. So sin theta is 90. Why theta is 90? Because we are using radial. By default, we understand it that we are using a radial magnetic field, and radial magnetic field is always at a 90 degree to the area vector of the coil, right? So let's see one more numerical. If we have a moving coil galvanometer has a flowing, yes, a moving coil galvanometer has the following particulars. That is the number of turn n is equals to 24. All right, we note it down. That moving coil galvanometer has a number of turns is equals to 24 turns, and the area of the coil is equals to 20 into 10 to the power of minus 3 meter square, right? And the magnetic field strength B is equals to your 0.20 Tesla, and resistance is equals to 14 ohm. These are the data being given to us. Now indicate a simple way to increase the current sensitivity of the meter by 25%. It is not easy to change A or B. So I already told you that current sensitivity alpha upon I is equals to N B A upon K, out of which K is fixed for the spring. A we cannot change as said in the question, and B also we cannot change. B and A we cannot change because it is difficult. So what is left with us is only n. We can change the number of turns. So if current sensitivity is to be increased by 25%, then the number of turns are also be supposed to increase by 25%. So if initially the number of turns is 24, then the 25% of it will be equals to 6. So the new number of turns in the coil, if we make the number of turns equals to 30, then the current sensitivity will increase by 25%. So increasing the number of turns in the coil by 25% will increase the current sensitivity of the coil by 25%, right? So this is the thing. Now let's move forward. So this was how the moving coil galvanometer is being made, and how it works, and how the current sensitivity and the voltage sensitivity of a moving coil galvanometer can be calculated. Now the next thing which we are going to study is how a moving coil galvanometer can be converted into a ammeter or in a voltmeter. So first we will see that how the galvanometer will be converted into an ammeter, right? So ammeter is a device that is connected in series with the circuit, and it measures the current flowing in the circuit. Now if the ammeter is measuring the current in the circuit, it means the entire current flowing in the circuit has to be pass through the ammeter, right? There should be no current loss, or there should be no distribution of the current. So we try to have a maximum current flowing through the ammeter. So if we want maximum current to flow through the ammeter, we should have minimum resistance of the in the meter, right, in the coil of the meter. So to minimize the resistance, we always connect resistances parallel, right? We are seeing in current activity that when the resistances are connected in the parallel, the equivalent resistance has a value less than the least resistance in the combination, right? So if we connect a very small resistance in parallel to the galvanometer, the equivalent resistance of the galvanometer will drop, and because of the drop in the resistance of the galvanometer, large current will flow through it, and we can measure the current flowing in the circuit more accurately. So the circuit diagram for it will be that if suppose this is a galvanometer, suppose this is the galvanometer, and these are the two terminals of the galvanometer, and if we connect a very small resistance in parallel to the galvanometer known as shunt, represented by S, then this combination will work as a ammeter for us, right? Now, suppose we connect this in the circuit, external circuit in series, then the current flowing in the circuit will flow like this. Let the current flowing in the circuit be I, and that current will enter into the ammeter. When it enters into the ammeter, a small amount of current, sorry, a large amount of current will flow in this, and we call that current is equals to IG. What this IG is? IG is known as full scale deflection, full scale deflection current, right? That is when Ig flows in the galvanometer will slow its full deflection. That is move from 0 to the last value, right? Then if Ig is flowing into the galvanometer, then the current flowing in the shunt will be equal to I minus Ig. I minus Ig. Now, if the shunt and the galvanometer both are connected in parallel, then we can say that the potential drop across the shunt will be equal to the potential drop across the resistance of the coil in the galvanometer. So we write it as S into I minus Ib is equals to G. Capital G over here is the representation of the resistance of the coil of the galvanometer, right? So G is the resistance of the coil of the galvanometer, and the current in the galvanometer is Ib, right? So if we need to calculate the value of the shunt, then the shunt will be equals to G into Ig upon I minus Ig, right? So this gives you the formula to calculate the value of the shunt, which will help you to convert a galvanometer into a meter, right? Now in this formula what we have is, first thing is S. This is the shunt which we need to calculate, which we need to connect to the galvanometer, right? G is the resistance of galvanometer, right? Then I will be the maximum value of current which we will be measuring with the galvanometer. Ig is the full scale deflection current, right? Ig is the full scale deflection current. Now, if we need to convert a galvanometer into voltmeter, we are converting a galvanometer into a voltmeter. Then, for that case, when we need a galvanometer, we want the entire potential to drop across the voltmeter itself. The voltmeter is connected in parallel to the external circuit. So whatever is the voltage dropping across the external circuit, the same voltage should drop across the voltmeter. So here we need a high resistance. So to increase the value of the resistance of the galvanometer, what we will do, we will connect a high resistance in series with the galvanometer, and that resistance we marked as IR. Then this combination will work as a voltmeter for us, right? So if the current entering into this is I, let it be Ig, full scale deflection current, then the voltage V will be equals to Ig into R plus G, right? So we can say that V minus Ig into G is equals to I into R. So from here we can say that V upon I minus, sorry, it's Ig, no? Ig. V upon Ig minus G is equals to R. V upon Ig minus G is equals to R. So this formula will give you the value of resistance which should be connected into the galvanometer in series to convert that galvanometer into voltmeter. So now what are these values? V is the maximum voltage which we need to measure, with the help of the galvanometer. Ig is again the full scale deflection current, and G, capital G, is again the resistance of the galvanometer, right? This is the resistance of the galvanometer. So what I mean by the maximum value of voltage or maximum value of current in a meter, suppose we say that we want a voltmeter to measure from 0 volt to 15 volts. So 15 volts. So the value of the V will be taken as 15. And for the case of ammeter, suppose they say that we want a galvanometer to be converted into an ammeter of range 0 to again 15 ampere. So this 15 ampere will be the value of I. This will be the value of I. This would not be the value of IG. I should make it very clear to you all that this is not IG. This is the value of the range of the current which is to be measured. IG is the full scale deflection current, and it will be mentioned in the question that for this the galvanometer shows full scale deflection. So to just understand it better, let's see numericals regarding your conversion of galvanometer into ammeter and voltmeter. Let's see this numerical. This numerical says that a galvanometer with a coil of resistance coil of resistance 12 ohm show full scale deflection for a current of 2.5 milliampere, right? So see here they have mentioned that full scale deflection current Ig is equals to your 2.5 milliampere, right? This is Ig. So we can write it as 0.0025 ampere. This is Ig. Then how will you convert the meter into a meter of a range of 0 to 7.5 ampere? So capital I will be taken as 7.5 ampere, right? And a voltmeter of range 0 to 10 volt, and we need to convert it into a voltage. So voltmeter of 0 to 10 volts, so we will be taken as 10 volts, right? And the galvanometer has a resistance of 12 ohms. So we can say that G is equals to 12 ohm. Now, for conversion from galvanometer to ammeter, we need to calculate shunt, and the shunt will be equals to G into Ig upon I minus Ig. So putting the value will be 12 into 0.0025 upon 7.5 minus 0.0025, and calculating this we will get your shunt S is equals to shunt comes as S is equals to 4 into 10 to the power of minus 3, 4 into 10 to the power of minus 3. This is the value of shunt which when connected to the your galvanometer will convert it into a meter of range from 0 to 7.5 ampere. Now converting it into a voltmeter. So when we convert this galvanometer to voltmeter, your R is equals to V upon Ig minus G. So according to the question, this R will be equals to V is your 10 volts, Ig is 0.0025 ampere minus G is equals to 12 ohm, right? So again, solving this will give you R is equals to 3988 ohm. This is the resistance which will connect in series with the galvanometer. It will convert the galvanometer into a voltmeter of range from 0 to 10 volts, right? This is how we calculate the value of resistance and the shunt which is to be connected to the galvanometer in order to convert it into a voltmeter or an ammeter, right? Let's see one more numerical. It says an ammeter of resistance 0.8 ohm, right? So we'll take it as G is equals to 0.8 ohm. Can measure the current up to 1 ampere. It means this 1 ampere will give its full scale deflection. So we'll take it as Ig is equals to 1 ampere because this 1 ampere is giving it a full deflection, right? So what must be the shunt resistance to enable an ammeter to measure the current of 5 ampere? We want its new range. The new range will be I is equals to 5 amperes. What is the combined resistance of the ammeter and the shunt? So they are asking you the shunt in the first part. So shunt is equals to your G into Ig upon I minus Ig. So shunt will be equals to G is 0.8 into Ig is 1 upon 1 minus, sorry, 5 minus 1, right? So this will give you shunt is equals to 0.20 ohm. This is the shunt. Now they are asking the equivalent or the combined resistance of the ammeter and the shunt. So R equivalent will be equals to R1 into R2 upon R1 plus R2. That will be equals to R1. Let R1 be the shunt, so it will be equals to 0.2 into R2. R2 will be the resistance of the galvanometer coil, that is 0.8 upon R1 plus R2, that is 0.2 plus 0.8. So this will give you R equivalent as 0.16 ohm. So the combined resistance is 0.16 ohm, right? So this is how we have solved this numerical. So here we end up with this second part of the magnetic effect of current. What if you have observed over here is that when a tip from my side is whenever you are solving a numerical for your practice problem, always while writing the numericals, solving the numericals, write the formula for the thing which you need to calculate. Writing the formula every time will make you remember the formula. You will not have to give another time or a separate time to remember all the formulas. Practicing the questions, and for every question, every time you are solving, even if it is the same formula, you write it every time, it will help you to remember the formula. And once you write the formula and write the data which has been given to you, right? The way I was writing here, like see in this numerical, I'm writing the data N, A, B, R. Writing every data will help you to see a picture that what all data is being given to you and which formula could be applied. Right? Seeing the variables, you will recall. It will be easy for you to recall the formula. Once you're writing the formula, after writing the formula, you will find that these all variables are being given and this variable is unknown. So you will create an approach to solve the numerical, right? I hope you're getting the point. If when read the numerical, because most of the time I find that most of the students have problem in approaching the question. So first read the numerical very well, write all the data given to you in the numerical with their respective representation of variables, right? With the variables, you write the values as I have written over here, right? Once you have written the variables, you will get a picture that what formula could be used, because you have studied that topic, you have studied various formulae for that particular topic for calculating different things. So if you know the variables, you can easily guess which formula could be used. Now once you have written the formula, you will find that suppose the formula has 5 variables. Out of those 5 variables, 3 variables have been given to you, 2 variables are unknown. So if 2 variables are unknown, definitely out of those two, one variable is to be calculated and the second variable must be given in the question indirectly. So you will have to first calculate that or find that second variable which is being given indirectly in the question, and then put that those values in the numerical in the formula, calculate it, and you will get the answer. So the very first approach to make your solving numerical easy is read it once, read it, then read it the second time. When you're reading it for the second time, write all the data given in the numerical in with the variables, with the respective variables, and writing this will give you a clear picture which formula is to be used or which approach is to be done, right? Because once you have the resources, I mean resources means the data with you, which you need to manipulate to get the answer, it will be easy for you to understand which formula to be applied, right? So this is a these are the steps if you follow, you can easily solve any numerical, whether it is a conceptual numerical or it is a logical numerical or it is a formula based numerical. Writing the data will give you a clarity, a much more clarity that what is to be done in the numerical, right? So this is the tip from my side for solving the numericals, because I saw a lot of comments in the comment box that they are having problem in physics. Physics is a problematic for them. They are not able to solve the numericals. They don't know how to approach it. The simplest way to approach the numerical is write the data, find the formula which is to be used, and then put the value and get the answer, right? So try to follow the step, go through the video, see the video very well, write the comments, what you understood, what you did not understand, write your comments. If you want me to give some extra anything or extra tips or extra numericals or extra tips to make physics easy for you, please comment it in the comment box. Once you comment it, if I get a good number of comments, I will be providing you with some tips to make studying physics very easily. It will be very easy for you to study physics. Because what I personally feel is physics is the easiest subject because you do not have to carry anything. If you understand it, you do not have to remember anything. Once it is understood, it is all done, right? So I would try to give that sense of understanding of physics and the numericals or the concept of this. But for that, I need something in return, that is in advance, that you put some comments in the comment box that you wanted, right? Yes, or yes sir, you wanted, we want to want an easier approach to study physics, right? A lot of comments, your comment will help me to encourage, it will encourage me to do something more in the lectures, so that these lectures become and the physics become easy for you, right? So that is all from my side. Please go and practice the questions, also practice the question on the NTA PYQ book, because it will also give you a clarity of approaching the questions, right? And have a nice day. Thank you.